Well, good morning, statisticians. I decided I'd make 8-1 again. I made it last night and I really struggled with like two of the problems. It took me a long time to remember how to do some of the stuff. And I think this is probably like, the most important chapter. So I think it just makes sense for me to do it again. Um, this is about hypothesis testing. This is like where it actually is, everything makes sense. Um, and we actually get to see real situations and we see if it's significant or not significant. I have notes already written, so I'm going to be like showing you them as I go through the chapter. But this is where it's really like we finally got to like a real situation where we have data and we can see if a test is significant or not significant. I'm going to do my best to make this stuff clear, but it's hard. Like it took me like an extra, I don't even know, like 35 minutes just to find out where I was making a mistake on one of these problems. So if you struggle with it too, guess what? You're not alone. This stuff is difficult. So the first thing I'm going to do is I'm going to share my screen and I'm going to pull up the book and I'm going to talk about everything that has to do with hypothesis testing. Hopefully it's as good as the other part that I made for this, but we'll see. We shall see. So here we go. Sorry, I have like a million emails. All right, so here's the hypothesis testing. And here were the problems. Some of them that I struggled with. I'm gonna be honest with you. All right, so I'll explain everything that I can. I'm a little more calm. I was kind of tired. So, what is hypothesis testing, right? This is the big picture. Understand it. We will describe the null and alternative hypothesis, significance levels, types of tests, two-tailed, left-tailed, and right-tailed, the test statistic, the p-value, the critical values, the statements, and conclusions. There's so much here. I would read this one really slow. In part two, they talk about the type of errors which happen. And in part three, they talk about the power. Now, all of these things are really important. Each one of them kind of has an idea. So we're going to start with just the very first thing they say. They describe a null and alternative hypothesis. I know I've spoke about this before, but if we have means, right, the null hypothesis or H0 just states that your mean one is equal to your mean two. Our whole goal for this stuff, our whole goal for pretty much whatever that we're doing in this is we want to reject the null hypothesis. That's our goal. Like that's what we set out to do. Our whole goal is to try to oops, sorry about that. Our whole goal is to try to reject the null hypothesis. That is our goal. And what do they mean by the null? That means there's no difference between the sample we got and the population. That's the whole idea. So our whole goal is we want to reject this. What does it say? Well, it's an example. Your mean one equals your mean two. Another way to think about this, that's if we have two separate means. If we have so there's no difference between the sample and the population, or there's no difference between here, your first group and your second group, right? You could put it like this, like X bars are sample and then the population mean, right? Because remember this X bar is your sample mean. And this guy is your population mean. That's another way to think about the null. Now, alternative hypothesis, this is our goal, right? Our goal for this is like what we hope happens. That's what they mean. What we hope happens. So we hope, and if it's two-tailed, we don't know which one's bigger. We're like, I don't know which one's bigger. And it changes the way that it makes it a little bit more difficult to prove. And we'll see that later. Or we'll say mean one is bigger than mean two, or mean one is less than mean two. What's another way we can write this? Our sample is not equal to the mean. Our sample is bigger than the mean, the population mean, or our sample mean is less than the population mean. That's another way that we can think about this alternative hypothesis. But this is our goal, right? This is what we hope happens. We're running this study because we think that there's some difference. And our whole goal is to try to prove that difference. Nobody's just going to believe us, right? Nobody's just going to believe us that there's a difference. All right. Now, what was the next thing they talk about at the beginning? All right. So the next thing that they talk about is the test statistic. Okay. So the test statistic we can think about as the critical value. So far, we have three of them. Our test statistics right now are these three things. We have our test statistic as a z-score, and we're going to use this for probabilities, right? Or percentiles. So that's what they mean by the test score. The other one that we have is the t-statistic, and this is the most commonly used one. This t is the most commonly used one. And the other one is, sorry, I don't know why I have this little thing at the top. I just have to move my floating head. And the third one we have, which we just found, was the chi-squared. Come on, get out of there. All right, well, I guess I just have to rewrite it. So we have our z-score, oh, our chi. So we have our z-score. I'm just writing it under it. And this is when we have percentages. And we're trying to relate stuff to the normal population. We've got our t-stats, which we use when we've got means. And we're going to use the chi-squared when we have what? Standard deviations and variances. So that's when we're using the three different types of these. They have tables, right? We're going to use tables to find them. If you suck with the tables, what can we use? We can use technology to find them. But that's like the most important stuff. Okay. So we did the two-tailed, left-tailed, right-tailed test. Okay, so the p-value and the critical value. Okay, so the p-value versus the critical value. All right, both of these we can get, well, the critical value is what we're getting from your t-statistic. Whatever, either through the tables or technology, the critical value is one of these three things. It'll either be your z-score, your t-score, or your chi-squared score. So this is the value of the test statistic. Basically, it's the value, and we just want to see if the test statistic, it falls in the range. The critical value, I'm trying to think. So we have our test statistic. The critical value is basically what we get from our confidence interval and our sample. Okay, that's what the critical value is. We get it from like the confidence interval and the sample. And our goal is to see if we have this critical value, right? Whatever it is, we just want to see if our test statistic is here, like kind of exceeds it. If our test statistic exceeds it, we're good to go. It's kind of the same thing for the p-value, right? Because remember, our confidence interval, like we have like kind of like a range, and we just want to see if it's like within the range. The p-value is the kind of same way. It's like if we're in a confidence interval, right? As long as we are outside of it, guess what? We get to reject the null. Isn't that so nice, right? As long as we're outside of that confidence interval, and our critical value is kind of like what the confidence interval is, we get to reject that null. Our p-value, we just have to kind of exceed it. As long as we're exceeding the p-value, we get to do what? Reject the null. And remember, that's our goal. We want to reject the null. We want to reject that null. Why do we want to reject that null? Because the null kind of just says, oh, that's funny. I have the same sorts of pictures. So the null's just kind of saying that there's no differences, there's no change. But if we reject that, we can be like, we are sure there is a change, there is a difference. And that's what the p-value or the critical values do. You could use either one. And I think that's where I got a little confused. All right, now we have the statements and conclusions. So usually our p-values, 9 times out of 10, it'll either be 99%, which is an alpha level of 0.01, or it'll be 95%, which is going to be an alpha level of 0.05. A lot of times we have to cut this in half, right? Because we're only looking at like one side of it. So if it's like a 0.05 and we want the alpha over 2, what do we have to do? We're really using 0.975. Not something that really happens, but these are the two most common. This one we use for medicine, and this one we use for like social sciences, like psychology and stuff. Because if it's medicine, we really want to be sure that what we're 1% sure, or sorry, we're 99% sure that this did not happen due to chance, right? This whole percentage business, this is like for chance it's happening. Okay. We talk about type 1 and type 2 errors. We talk about power. All right, so the statement is basically that it's like we are sure not due to chance something something something. And the conclusion is like what we say about it afterwards. In part two, we do type 1 and type 2 errors. So this thing gets messed up all the time in statistics, type 1 and type 2 errors. So a type 1 error is basically we reject the null. Okay. Okay, here we go. All right, so this type 1 error, okay, this means we reject the null, but the null was true. What does that mean in real life? We thought we found a difference, but there is no difference. Thought we found a difference, but there is no difference. I think this is worse. I definitely think this is worse than a type 2 error. Okay, so when they talk about type 2, right? When they say type 2, okay. When they're talking about type 2, they're talking about type. I lost my power to draw. Try that again. Maybe I gotta reload the page. Things happen. We're in Intro to Stats 8.1, and I'm just adding on to the notes. So when they're talking about type 2 errors, it's kind of like the opposite, okay? So a type 2 error, this means we did not reject the null, but the null was false. This means we claim there was no difference, but there was a difference. You could tell me about which you think is worse, I think type 1 is worse. You're saying that you found something, but there was nothing there. Here it's like, well, we didn't find anything, but there was something there to find. Like that's also really bad, but it's not as bad as claiming there's some phenomena out there when there really isn't. Okay. So p-value, there's your critical value, not significant if you're over here, it's significant. Okay. All right, let's keep going. Let's keep going. So that was like a little bit of intro. I hope it was clear. Try my best to make it clear. So a hypothesis is a claim or statement about a property or population. And the test or test significance is for trying to find that out. That's a good definition. All right, so this is what they say. Most internet users, more than half, utilize two-factor authentication. Okay, that is their claim. And so their null hypothesis would be there is not, most internet users do not use it. Like you could just say that there's an equal amount of internet users that use this, right? It would just be P is equal for this one and be like your hypothesis would be that it equals that. Um, and then the change would be 0.5 and root point or not equal to 0.5. This one would be the mean body temperatures is less than 98.6, and null would be the mean of body temperatures is equal to this, but we're saying that there's a change. We're saying it's less than that. So this is one-tailed, this is one-tailed. The population of college students, and this is the first one. This is for z-scores. This is for t-statistics. And this one is for standard deviation or chi-squared. That's why they're showing you the three different types. Why do I keep getting emails? All right, so here we go. Here's our example. Consider the problem. Most internet users utilize the two-factor authentication on their data. Okay, so how do we write this? Your null hypothesis is 0.5 and your Q is 0.5 because we're going to use the Z statistic. So remember with the Z statistic, it's that crazy formula. I believe it is for your Z statistic, it is whatever the value is. I believe it's the square root of P times Q over N. Be sure what that's what this one is. Oh, that's the bottom. I knew that there had to be more to it. So this is your what? This is your sample. This is the probability of it happening over the square root of it happening times it not happening over n. And this is going to give you your z statistic, which is really nice. And then you look up the z-score and you see kind of if it matches. And I'll go through all the formulas too. Perfect. Okay. In the chapter problem, we have survey results saying 52% of 926 internet users. And if we had 50.1%, it's not significantly high. 925 is significantly high, and unclear, it's so we're not sure. Like it's either going to be not high, which is about the same, significantly high, or we're not sure. So what does stats do? Stats allows us to actually test this thing. So let's test this one. We might as well. So basically, let's say we want to be 95% sure, right? Let's use that as our alpha level because this is in medicine, right? So we can find the t statistic going this way, right? Or we could use technology. So for our z score, for our z test statistic, all I have to do is take the sample, right? This is our parameter of the sample minus the and we have enough people, 926, as long as it's bigger than 30, right? Minus P over the square root of P times Q over M. So remember, this is the value we get from our sample. In our case, it's 52%. Our P value is what? Well, they say 0.5, right? We just is 0.5, it's yes or no. So that's 0.5 times 0.5, because if yes is 0.5, no is 0.5, and we're dividing this by 926. This is going to give us our test statistic. So let me pull up Desmos. I have Desmos. Here we go. As you can see, I was working on it before. So 0.52 minus 0.5. And I have, what is this? I have zero point 0.5 times zero point 0.5, zero point 0.5 times zero point 0.5. And how many people are in this? 926. So we get a z-score of 2.43, which is useful, but we have to know what that means, right? We want to be 95% sure. So we can go to StatCrunch. And how did I get here? We can go to StatCrunch, calculators, normal, because the z-scores fall in this normal standard deviation. And we just want it to be what? Less than 0.5. They said less than, right? This is a one-tail test. Yeah, so we just want to be like, there's more than that, right? So we're only looking at one side of it, and that changes things, right? This is going to change something. So I'll also show you on the table. So 0, 1, this is the normal distribution. And the first thing we just need is we want 95%. So equal to 0.975, because we're usually cutting into both of these. This is 2.5% on one side, 2.5 for the other. So I believe it's just 0.975. So we have to be here a z-score of 1.96 is what we want. Ours is 2.43. So we're over here. Um, it looks like we are past it, right? So I believe this is significant. So let's see. I could be wrong. So it's easy to obtain hypothesis testing results when using technology. So we need the test statistic. Examining the screen say we say common test statistics of if z equals 1.25, we have this p-value. The results of the t-statistic p-value are important, but understanding the hypothesis testing procedure is far more important. Yeah, so understanding how this hypothesis testing actually works is most important. They are using, they're going to use StatCrunch. Okay, so let's see how StatCrunch works. We want a one sample proportion of hypothesis statistics. They say it should just be 1.248. Okay, let's see. Uh, let's see. Our sample mean is what? And do we have a sample standard deviation? I don't think we could go this way. So let me go right back to the book. It says a one sample proportion summary based on these. It says we have 482 people out of 926 people. Maybe I could do with powered sample size. No. What does it say exactly on the top? It says one sample proportion summary hypothesis test. All right, here we go. So how'd I get to that? I went to stat, proportion, stats, one sample, what summary, the number of successes. Well, we don't have any number of successes. It just says it was 0.52. So we know 0.52 times the total, 926, is 48.1.52, but I'm rounding it to 482. You can't have a quarter of a person. You always round up for ends and things like that. The number of observations was 926. It's equal to 0.5. And we want to say it's going to be greater, right? We want to say it's more than that. And I want to show the critical value. Make sure I did that right. Let's compute this thing. So 482 out of 926, the sample population is 0.52. That's what I said. There's your error. Our z-stat said was 1.24, and our critical z was 1.64483. Okay, so it's not significant because this is 10%. I got a different one for my z-stat and my critical. Okay, well, because it was one-tailed, if I change this to 0.95, and I swap that, sorry. Okay, so that's how they got the z-stat. So 0.95, they're saying it's just one tail, so we're just looking at this one side. So that's how they got the 1.644. But how did they get the z statistic? How come there's this 1.2 and minus 2.43? Well, I'd rather be able to see it by the formula, right? Um, let's see exactly how they got it on the formula. There's their z statistic, 1.24. Our z statistic was 2.43. So we made a mistake somewhere, but that's okay. We all make mistakes, right? So they say this is 0.52. All right, let's just try it again. I could have just typed it in wrong. So I have 0.52 minus 0.5, 0.5 times 0.5 over 926. Let's look at the formula. Okay, this is the one we want to use, this normal one. Okay, so sample mean minus the mean, minus what could happen over PQ divided by N. So we have 926.5.5, and this is 0.52. All right, what's the only other way to get this statistic? Well, we don't have a standard deviation, so we can't do it this way. So the test statistic is this parameter minus the P, which is what we wanted to find, 0.5 times 0.5 over N26. Oh, okay. This is why it's different. No, the count is still 926. 5.2. Well, we got it in StatCrunch. I don't know why I can't get it by hand. All right, so I have 0.02 on top, bottom is 0.5 times 0.5. That's it happening versus not happening. And then we have, okay, so it's really just 0.02 divided by, oh, I have the square root in the wrong place. Oh my God. Sorry. The whole thing is supposed to be square rooted. I already see it. See, a little mistake, right? And the whole thing goes to hell. And that's okay, right? The whole thing is square rooted, not just the bottom number. And there's that 1.2 we were talking about. Now 1.22. Okay, so we know our z-score is 1.644. Where did we get that? It's 95%, but less than. There's our 1.644. We got 1.22. We're here. See how the 1.2 is like kind of like right there? But we want to be here. We want to be more than that. That's why we're going to reject it. And another way to look at this, as long as this number is not bigger than 0.05, I mean, not smaller, sorry, not smaller than 0.05. This is using the critical value, right? So our critical value is here. It's 1 point, we know we have to be what? Past 1.64. We have to be in here to be significantly different, but we're not. We're here at 1.22. That's why we're rejecting it. Now, because this thing is less than 0.05, I mean, not less than 0.05, we're also rejecting it. Let's see what the book said. Hypothesis tests are also called tests of significance. This chapter is those. We will proceed to conduct a formal test of example one. Okay, that's fine. All right. Oh, and then they go through all the things. So we identify the claim, give the symbolic form, identify the alternative and null hypothesis, select the significant level, usually 0.05 for social science, 0.01 for medicine, identify the test statistic, and then we decide. We either use the p-value. So we reject it. We reject the null, which means what? There was a difference. If we reject the null, it's something good that we like. We reject the null if it's less than 0.05. Now, we reject the null if the test statistic is in the critical region. We go back to our picture, you can see we're not here. We're not in the critical region. We're outside of it. Guess what? Rejection. We're not less than 0.05. Guess what? We cannot reject it. We fail to reject the null, which basically just means that nothing happened, right? Nothing happened. It's just the same as, and then we just say it. We make a decision. That's what that crazy chart is for. Okay, confidence interval method, one-tailed test versus two-tailed. 0.01 is 99% sure, 98% sure, and then we have the two sides. Okay, so let's keep going. All right. Here are the three formulas. All right, so the null hypothesis is H0. The alternative is H1, HA, or HA. Which did I use? I used H1, but you could also use HA. That's fine. Use H1 if you got a couple of different ones there. That's fine. The null hypothesis is what normally is there. I don't like this hint. I think the best way to think about this null hypothesis is what's there already. The null hypothesis means there's no difference or no change, and your alternative means there's some difference or change. Null, nice. These are the three. This is one-tailed, one-tailed, two-tailed. Okay. So for the one that we did, 0.5 was the null, and then we wanted to see if it was something greater than that. And we found out that guess what? Based on our data, it wasn't in the critical region, right? It wasn't past this number. We said that we got 1.64 because we're less than the 95%. And we wanted it, but we just got, look, 1.22. That's why we had to reject it. All right, selecting your alpha or A. So this is basically our alpha or A is the p-value. Okay. What are we going to reject it? Usually it's 0.05 for social science, 0.01 for medicine. That's what that means, okay? Used as the cutoff for determining where it's significant. So we get to make that choice, right? We're allowed to make that choice, which is really nice. Common choices are 0.05, 0.01, and I've never really seen 0.10, but it happens. 0.05 is the most common. Okay, so here are our formulas. Let's go over all the parts of these formulas just to make sure we know them. All right, so the means is the one I use the most, okay? So this means what? This is your sample mean minus your population mean over your sample standard deviation over the amount of people you studied. That gives you your t-score. Okay, this gives you your test statistic. This is the one I just did. This is the value you got for your parameter statistic for what, how many people said yes versus no. This is the percentage of people of it working. This Q is the percentage of it not working over the amount of people. You could also get a z-score with means, but that's only if we know your sample standard deviation. Sometimes you don't, right? Sometimes you don't know it, but that's another way to use z-scores to get the mean. And finally, your chi-squareds. Your chi-squareds are what? That's when we're using to find standard deviations. That's basically the difference between them. So your chi-squared is basically your total minus 1 over what? This is that's your sample variance over what? Your population variance. That'll give you that information, okay? That's what those parts are. Now, can the computers do it? Yeah, we just did StatCrunch, and StatCrunch just spit out that 1.248 value for us. And we could see, though, right, that we got the same thing. We got this 1.2. We got 1.22, which is close enough to the 1.24. It's just because they're super precise. I believe that's the only difference. Okay, let's keep it going. Like you see how ours is 1.66485. Oh, these match because they're the computer doing it. Okay, let's keep going. Okay, so the test statistics gives us the measure of the amount between the sample and the population. That's all these three things do. They're just telling us the difference between the sample and the population. That's what these three things are, okay? For proportions, we make this discrepancy between the sample proportion and the population. So the test statistics is the value used in making a decision about the null hypothesis. It is found by converting the sample statistic. So whether it is the sample proportion, your sample mean, or the sample standard deviation to a score such as a z, t, or chi-squared. We do this so we can see if it's true or not. We're turning whatever we want, whether it's the mean, the proportion, the standard deviation, into a value where we can test it. That's where it gets confusing. All right, so for example 1, we have a claim about the population proportion P. We have N is 926, P is 0.52, the null hypothesis 0.5. So if our P is 0.5, if 50% of the people have it, then the Q is also 50%. That's how I got that other number. Okay, and the test statistic is Z is 1.25 from the technology. Each of the previous technology displays a more accurate result of 1.22. Okay, so if we replace, okay, so if we actually use this 0.520, blah, 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 that's how we get the 1.25 instead. That's the only difference. All right, cool. More emails. 1.22, is that what I got? And sweet, it's the same. I like it. All right, so the tails, right? The tails. So the critical region is the area responding to all values of the test statistic that will cause us to reject the null hypothesis. So where's your critical region for this guy? This is it. There's your critical region. We're outside of it. So basically, we want to find it. Two-tailed test, it has both extremes. We've got the left-tailed test, the right-tailed test. So when it's not equal to, it's this one. We wanted it to be greater, right? Our hypothesis is greater. That's why we're just looking at this side. That's why we're just looking at that side. Okay. Now the p-value method is we just look at it, right? We just look at over here and see if it's less than that 0.05 that we want. This one, the p-value, I'm not really sure how to do that by hand. I'm sure there's a formula somewhere, but I'm just not sure. I've always, whenever I've done this, I've always just looked here at the very end. I always calculate this by hand. And this I sometimes use the table for. I've always used the table for this. I've done this by hand, but the p-value, I'm not really sure where the formula comes from. Let's see if they give it to us. The probability of getting a value of the test is least extreme. That's fine. So the probability of getting a test statistic at least this extreme is 1 pound of sample data to be true. And they're saying that you're using P for like everything. So don't mess it up. To find the p-value, find the area beyond the test statistic using technology or A-2. Then use a procedure given in A-3 that can be summarized. Okay, so left tail, area to the left of the test statistic, to the right of the test statistic, and then the critical region is twice the area beyond the tail. This is the thing that I messed up because for when it's two tails, you actually have to double that region. That's why I messed up when I was doing the problems the first time I tried this. I didn't double the area beyond the test statistic. So don't make my mistake, right? We all make them, but I just didn't double it. So see how this is here. So there's the p-value is twice that. The p-value is what it is. So we actually have to twice the area to the right, twice the area to the left. That value that we get, we have to double. That's the one thing you got to remember. Okay, so using the example, we want to the right, it has a p-value of the test statistic is 1.25 or 1.22, which we got, and the p-value of 0.10. The p-value differs slightly from this one. Okay, that's fine. Okay, so the standard method of testing the hypothesis and using the p-values have widespread acceptance and use. They say p-values are a lower excuse. No, they want you to use the test statistics every time instead of the p-value. On my dissertation, I got away with using the p-value, but it's up to you. The critical value method is the traditional method for doing this. So the critical value separates the critical region where the null hypothesis from the values of the test statistics that did not lead to rejection of the null. Okay. Separates the critical region, not tested. I like it. So this was ours, right? This was the 1.22, but we need the 1.645. Anything past this is what we wanted. But because we're less than that, what do we have to do? Reject. So here we go. If the p-value is less than your alpha, the null must go. Yeah, so our p-value is this less than 0.05? Nope. So the null stays. We cannot reject the null. And we fail to reject the null. And, oops, sorry. And if our p-value is greater than that, we fail to reject the null, which means what? That's what we want. So if it's bigger than that, which we have, we fail to reject the null, which is nice. And this is for the critical value method. So if it's in the region, right? If it's in that region here, we reject the null is what we want, right? That's the whole idea is what we want. But if it's outside of the region, we get to reject it. So we're here, we can't reject it. If we were here, we would reject it. So if this was bigger than 1.64, we would reject it. And when say that, and we could say in our case, there is a difference. There's not significant evidence to support the claim. Yep, there's not significant evidence to support the claim. I like it. So this is exactly how you want to word it. It's different based on like which test you do, but you could say there's not significant evidence, there is sufficient evidence. You could look through these and say exactly what you'd like. We're not using except, not using multiple negatives, just use this wording. There's not sufficient evidence to support the claim that. There is sufficient evidence to support the claim that. There's not sufficient evidence to warrant rejection of the claim that. There is sufficient evidence to warrant rejection of the claim. Yes. Use this chart and just write it how they like it. APA and like medical journals are very specific about how you have to word these things. All right, now we've got confidence intervals. Did I talk about that in this? Those are the errors. I guess I skipped this part. Confidence interval of the population parameter contains the likely values of the parameter. We should therefore reject the claim that it has a value that's not included. It's just another way to say it. Are they always going to be the same if you use confidence intervals? Proportions? Nope. Means, yes. Standard deviations? Yes. Okay. And then we could bootstrap or randomize or resample just to make it happen. Now, here are the errors. I know I tried to explain this before, but just remember, type 1, we claim that we found significance where none exists. And type 2, there is a significant difference, but we did not find it. So that's the most important thing, right? That's the most important thing is I think making a type 1 error is way worse, but that's up to you. Conclude that a new medicine is effective when it's really not, or conclude that a new medicine is not effective when it really is. That's pretty good. They have a little table. This is what you want. This is your mistakes. All right, how can we control for type 1 and 2 errors? Well, type 1 errors, usually we just make a really big sample. Or we shrink the alpha, right? Those are ways that we can do it. So if we change our alpha level, it'll probably help us from making this type 1 error. If we have more and more people, the chances of us claiming we find something when it's not there won't happen. So we have alpha, beta, and sample size are all related. So if you choose any two of them, the third is automatically determined. Okay. Consider the seriousness of a type 1 error. That's probability A. Type 2 errors are beta. Okay, so beta is the difference with not there. That's our effect. So this thing is really important. Like I always use Cohen's effect size for this, but basically it'll really help you. So that's what power is about. You know sorry. So we increase the power, or we increase, usually we're just increasing the n to be able to find a difference when there is actually one there. So that's what beta does. That's what beta helps us do. It helps us fail to reject a false null. I know, is that wording so strange? So basically it's saying that if there is a difference, we will find it by beta, by making sure we have a good beta or having power. Power is like the generalizability of it. The power of hypothesis test is a probability, 1 minus beta, of rejecting a false null hypothesis. The value of power is computed by significance level alpha and a particular value of the population parameter. That's what it means. Consider these primary results for XORT. There are 13 girls among 14 babies born. If you want to test the claim that girls are more likely using the XORT method, All right, so alpha is 0.05. Values of the alternative values are what? Either 0.6, 0.7, 0.8, or 0.9. All right, so here's our power. So if we went with 0.6, the power is 18% of finding it, or 82% of it, 18% of it not occurring to the chance. 0.7 would be it's 43% not occurring to chance. 0.8 would be 77 not occurring to chance. And this would be we were 99% sure it's not short of chance. That's what this is asking you. So there's a 0.436 probability of rejecting this. Sorry, give me 1 second. Okay, so we can calculate power by doing this. 0.80 or 80% is usually the for power, which makes sense. They don't really give us one to try. That's okay. I've always just used a G-power analysis for this. If there's a question on it, we can do it. Here's a statement. The trial assumed that 0.05 significant level, 153 randomly selected subjects would be needed to achieve 80% of power to change the heart rate from 0.5 to 0.4. It has a good significant level and power level. The researchers decided that a reduction of the proportion of disease is an important difference. Use the significance level to find it. Cool, I like it. What do we got here? They got 153 people. All right, we're at the end. Could I do this by hand? I'll hear the questions. So I'll put them on the side. We'll see if I make mistakes. But here we go. Here are the questions. All right. Here's number one. A formal hypothesis test is to be conducted to test the claim that the wait times at Space Mountain rides will have a mean equal to 40 minutes. The null is, guess what? Our mean will be equal to 40 minutes. Nice and simple, right? That's what the null hypothesis is. In words, the wait times at Space Mountain ride is equal to 40 minutes. The alternative hypothesis is, okay, it's just not equal to 40 minutes. So this is two-tailed. So basically, this first one is the mean is equal to 40 minutes. It's not equal to 40 minutes. What are the possible conclusions that can be made about the null hypothesis? It's either going to be 40 minutes or not. Is it possible to conclude that there's to support the claim? I don't know what D is. I can look it up. So we could either accept or reject this based on what we have. And is it possible to conclude that there is sufficient evidence? There is sufficient evidence? No, we could either fail to reject that claim. We either reject the claim or fail to reject. So D is no. Your two choices are reject your H0 or fail to reject H0. That's what this means. Because stats, we can't be super positive about it, right? We can't like really know it unless we actually do it ourselves. All right. So the labels on cans of Dr. Pepper soda indicate that 12 ounces of the drink. We collect samples of those cans and accurately measure the actual contents. Then we would use methods of 7-2 for making an estimate about the mean amounts of cans. What is the difference between estimating a mean and testing the hypothesis about the mean? Okay, so when we're doing that estimation, like we did on the last one, we're doing estimation like we did on the last one. We just get a confidence interval. Like we know it's between these two values, right? We are 95% sure that the mean is of 12 ounces is between these two values, right? That's what we could do for this. Now, for hypothesis testing, sorry, my allergies going crazy. For hypothesis testing, we could say it's 12 ounces or not. We'd either say it's equal to 12 ounces or not. This time we get like an estimation. We get a whole range of answers. That's what they want. And you can word it in any way that makes the most sense to you. We get a full range of the values. This one, it's either going to be, we're either going to fail, we're either going to reject or fail to reject the fact that the mean is equal to 12. That's the difference. We're either 95% sure it's in the range, or it's this is the mean, or this is not the mean. All right, let's go to 3. All right, the Erickson method is one of the several methods claimed to increase the likelihood of a baby boy or a baby girl. The clinical trial results could be analyzed with a formal hypothesis tested 0.5. Okay, which is to increase the likelihood of having a girl. If you have an interest in establishing the success of the method, which p-value would you prefer? Well, 50%, oh, that's just the alternative hypothesis. So if you want a p-value and you really want to make sure it works, 0.05 is the most common for something like this. This is the most common, and it's the easiest to prove. Now, if you're trying to test out a drug, you'd be using 0.01, like test a drug or test medicine. I don't know what this Erickson method is. If we have 0.001, though, it's like the strictest. This is the strictest way. Like, we are definitely sure here. We are 99% sure if we use this one. So, which will we prefer? We'd always prefer the 0.001, but most of the time we use 0.05. All right, let's go to 4. A bottle contains the label starting that 500 milligrams of vitamin C. Another contains 40 milligrams that's used to treat high blood pressure. So vitamin C or blood pressure. Identify which of the following errors is most serious. Okay, so type 1, type 2. What does that mean again? Type 1 is there is no difference, but we claim there is one. And type 1 is there is a difference, but we don't see it. I want you guys to do this one yourself. So really think about this. Do you think having the vitamin C or something used to treat high blood pressure, which one do you think is more important? I obviously think this Merck pills, and I actually own a lot of Merck stock. I think it's really fun that it's in it. So I think the medicine is more important than the vitamin. So I'd go with Merck. And what do you mean by type 1, type 2 error? You decide. All right. I'm going to let you guys give me a good reason for that. So that's 1 through 4. All right. Now it's about to get more tricky, and I will explain them. All right. So 6, 7, 9, 11, 15. All right. So let's go to 6. And as usual, and I want these in a place where it makes sense for you. All right. So here's number 6. 6, 7, 9. Let's do 6. Identify HO and H1. Okay. And identify the null and okay. So 6 is most adults know that a light year is measured distance. A Pew Research Center 3,270 adults, 72% knew that a light year is measured. So the original claim is most adults know that a light year is a measured distance. So that's P is greater than 0.5. It says most, so it's more than half. The null hypothesis, your null hypothesis would be P is equal to 0.5. And because they say most, P is greater than 0.5 for 6. Do we have to do anything else for this? Nope. Okay, what's a good 7? The mean systolic blood pressure. Okay, now we're doing means. So now I have to use this. So this would be which statistic? This is a Z statistic. This one's a T statistic. So this one for number 7. Number 7 is what the mean is. The claim the mean is less than 123. All right, so our hypothesis is the mean is equal to 123, and your alternative hypothesis is that your mean is going to be less than 123. I'll look that up, make sure that's right. Nice, that's right. All right, let's look at number 9. So number 9, find the value of the test statistic. Okay. All right, so number 9. So we have to do, what are the other ones? So I could write them all out. You got to go 9, 11, 15. For these two, we're doing 9 and 11. Let's do 9 and 11. Let's go to 9, and then I'll do 11. Number 9. We're doing landline phones, okay. Fewer than 10% of a phone only have a landline. All right, this is another percentage one. So fewer than, so that's 10%. So our null is going to be this P is equal to 10%. And we want fewer than, so our alternative hypothesis is going to be P is going to be less than 0.10%. So we need to get our what? We need to get a Z statistic, and we need a Z score. And let's see if this actually works. So let's do the formula. So the formula is what for Z statistic? It's P hat minus P over the square root of the whole thing, P times Q over N. All right, so our P hat is 5.8%, or 0.058. Okay, and we're testing 10 minus 0.10. This is what we want. This is it happening. This is what we're testing. So we're saying 0.10% has it. So if 0.10% has it, 0.90% doesn't. That's our Q. This is yes. This is no. And our N is what? Our N is 16,113. Notice this is bigger than 30, so we can do this. As long as it's not chi-squared, we don't have to test if it's normal. So let's put this in a Desmos. So we have 0.058, 0.10, 0.10, 0.90. How many people do we have? 16113. All right, so here's this. This is our Z-score. So this is our test statistic, which is negative 17.77. Cool. Now, all I need to do is go here and get the actual value, right? So our value is what? How do we get that value? Well, we want to be 95% sure, but now it goes the other way. I believe it looks like this. Cool. So this is it. This is our P. This is our value right here, right? So we got negative 1.644. Is negative 17 past that? Oh, yeah. So we're going to say this is significant. So what are we allowed to do? We can reject the null. And let's actually change this one too to see how it works here. Let's make sure this is going to be less than 0.05. Let's edit this thing. So how many successes do we have? Well, we don't know exactly. So it's 0.058 times the total. Times the total, which is 16113. So 935. That's what we're using. Why? Because we can't have a decimal of a person. You always round up. And our number of observations are 16,113. Hypothesis testing, we're testing 0.1, and we want to be less than 0.1. Show the critical value, compute. All right. Our z-stat, negative 17.77, yes. Our critical z, negative 1.644, yes. Is this less than 0.05? Yes, we did it. I'll check it in the book. Nice. So we got this right. Isn't that exciting for us? Hopefully that was clear. That was like a whole one. It's exactly how you're supposed to do it. I don't know if I have to do any more, but oh yeah, the two-tail was the one that I messed up. So I'll definitely at least get there for you. I did them all on the last video and I struggled. All right, let's go to 11. All right, let's go to number 11. Let's see what 11 has in store for us. 11, we're doing blood pressure. So this is number 7 here. All right, the mean. All right, so we're doing a t-test here. So we got to use the other statistic, the other formula. We're doing a mean. Mean of a healthy blood is less than 123. So our null hypothesis is that basically our mean is going to be equal to 123. Our alternative hypothesis is less than, so this is not two-tailed, it's one-tailed. So now our mean is going to be less than 123. Our n is 300. And our sample mean, like the mean that we want, the one that we got from our sample is 122.96. And we have a standard deviation of our sample, so that's just our S squared, right? For standard deviation, oh, sorry, that's variance. For standard deviation is 15.85. So let's go to that formula. Let's go to what the formula is and work it out. Here's our formula. So the t statistic is going to be our x bar 122.96 minus the 123 divided by 15.85 over the square root of 300. All right, so let's see what that is. 122.9, I need parentheses. 122.96 minus 123 divided by parentheses 15.85 divided by square root of 300. So our t statistic is really small, negative 0.02. Right, that's our t statistic. So now we also need the table or the normal value for this. Or we could just use this, right? We could just use the t-stats one sample with summary. Our sample mean was 122.96. Our sample standard deviation was 15.85. Our sample size was 300. Our hypothesis test is this should be 123. And we're going to go one tail, so it's less than 123. And we're going to compute this. We got negative 0.02. They got negative 0.04, which is fine. They got a p-value of 0.4. Is that less than 0.05? Nope. So, not significant. Fail to reject the null. Ta-da! Now, if we wanted this, I think that's all we can do for this one. All right, let's go to the next one. Let's go to 15. Did I do this before? Oh, okay. Well, number 11. I got negative 0.043. Well, that's what it says here. Did I type it in wrong like a fool? Oh, I put a 25 instead of a 15. Man, now it's the exact same answer. Negative 0.043. Cool. Cool. Failed to reject the null. All right, let's go to the next one. All right. And the next one we have to do is number 15 and 16. Let's do number 15. All right, here's number 15. The test statistic is this. When obtained through this. Okay, so this is the one that I messed up that freaked me out. All right, so identify if it's one-tailed, two-tailed, left-tailed, or right-tailed, because it's not equal to this one. This one's a two-tail. All right, find the p-value. So it says that we have a z-score of 1.80. So we have to find this p-value. Now, this is where it gets a little confusing. So it's two-tailed, which means it's going to be a little challenging. So basically my z, we know it's 1.80. Oh my God, sorry. So I have this value, right? This is one side. I have 0.0359. But I have to do what? I have to double it for another tail. So I have to multiply this thing by 2. That was the error I was making every time. So if I double this, 0.0359 times 2, you get 0.0718. So there's our value. There's our statistic. And I don't know why I couldn't figure this out. So we have 0.0718, which is, that is our value. Now we have 1.80. Oh, sorry, we have to look at our p-value. So our p-value is 0.314, right? It's bigger than this. It is bigger than that guy. So if I have 0.0718 and I have 0.314, I gotta fail to reject because our p-value is bigger. Let's double check that. Fail to reject. Nice. All right, I might as well show you 13. Here's 13. Now our z is negative 0.75. Because we're using the 0.05 level, right? We're using 0.05. Sorry. The reason why we're rejecting this is because we're using 0.05 and this is bigger. That's why we're rejecting it. My bad. The 0.314 doesn't really mess with us for this. And this one, we already could see it. So let's do this one. So this one is P is less than 1/3. I might as well show it again. So P is less than 1/3. So this is a one tail. So we can go here. Now I have a negative 0.75. Okay, so we have a negative 0.75, but we want to be less than that. So I have a 0.2266. Now, is this thing, we're left with this 0.266. Is that bigger than 0.05? Yes, it's bigger, so we failed to reject. Let's up 13. That's full. For some reason, I kept like not being able to wrap my mind around this when I did these before. All right, let's do a couple more, and I'll leave the rest for you. Let's do 19. All right. Refer to exercise 15. Find the critical values. And I'll let you try these. This is cool. I'll let you do these. I did these before, but I'll let you try them. So let me do 19. So 19. All right, so 19, we're doing exercise 15. All right, so we have to find the critical value here. So 19, we have to find our CV, and then we have to see if we're going to reject the null. All right, so let's look in 19 is 15. So we have a z-score of 1.80. Oh, I'm gonna pause this for 1 second. And then I will get back to it. Hi, so here's the last one I'm gonna do. I said I do 19 for everybody. So let me share my screen. This will be the last one that I do. So 19, we have to find the critical value. As long as we find the critical value for 19, we should be good to go. So for number 19, it's basically using a 0.05. So to find that critical value, I know that as long as I have my 95 percentile here, sorry, but it's got to be a probability. You could see that if I'm in a 95%, it's going to be 1.644. And I believe that is the answer for this one. Yes. Okay. And then in case you want to see this for 17. So for exercise 13, oh, we have to find the critical value. So if we're using this one, this is a one-tailed test instead of a two-tailed test. So basically for this one, going to be 0.925, sorry, 0.9. Well, the reason why this one that we did for 19 is in two directions is because it could be on this end or it could be on this end. That's why it's broken into halves. I think I have it over here though. Just try your best in the last two. I did 16 as well. 1/3 is 0.33, which we got 0.22 is failed to reject. Nice. All right. So try your best on these last couple. I'm sure you're gonna do just fine and enjoy your day.